The goal of this video is to explain the strangeness of quantum mechanics by talking about Bell's inequality. Since there's so much justifiable confusion around this, I'll try to go slowly and use as little math and as few technical terms as possible. Still, if I do mention something with a name, I'll try to put it on the screen in purple, but feel free to ignore that. There's two parts to this video. In the first, we'll look at the experiments that lead us to these conclusions. Then, in the second, we'll discuss the three options that these experiments leave us with. We must choose one, and each is more disturbing than the last. Suppose we have a measuring device and a particle. When we send the particle through the measuring device, we'll get one of two outcomes. Either the particle will go with the axis, which we'll call spin up, or the particle will go against the axis, which we'll call spin down. We can rotate our measuring device and send the particle through again. We'll still call it spin up if the particle goes with the axis, even if it's down on the screen. In this video, we'll consider measuring the particle along three different axes, which we'll call A, B, and C. Now, instead of one particle, suppose we have two that we send through spatially distant measurement devices. Further suppose that these two particles satisfy some experimental facts. First, whenever we measure them along the same axis, we find that they have the same spin. This means they always either both go up or both go down, but never one of each. This is true along axes A, B, and C. Second, whenever we measure the particles along different axes, we find that one goes up and the other goes down. Here are a few examples. While these facts may seem a little abstract or unintuitive at first, they're really expressing the simple idea that the two particles tend to go in the same direction. For example, if we measure particle 1 along the A-axis and find it to be up, then particle 2 will be down along the C-axis, up along the A-axis, and down along the B-axis. I should mention that there aren't real particles that satisfy these facts exactly, but they're a useful stepping stone because they're significantly simpler than the real facts that we'll talk about in a moment, and they still contain most of the interesting physics. For now, let's make a few assumptions and see if we can reach a contradiction. First, the particle spins exist independently of measurement. Taking the last example, this means that there really is a particle that has the property of being spin up along A and down along B and C. The squares denote the spin of the particle, filled being spin up, and empty being spin down. The second assumption is that the axis we choose to measure particle 1 along doesn't affect the properties of particle 2. Now let's reach a contradiction. Recall that we got this state of particle 2 when particle 1 was up along A. If we had measured particle 1 along A and instead found it to be down, then particle 2 would have to be down along A, but up along B and C. Now suppose that instead of measuring particle 1 along the A-axis, we measured it along the B-axis. In this case, if particle 1 is up, then particle 2 will have to be up along B and down along A and C. On the other hand, if we measure particle 1 and find it to be down, then we know that particle 2 must be down along B but up along A and C. Now we've reached our contradiction. If we measure particle 1 along the A-axis, then particle 2 is one of these two states. If we measure particle 1 along the B-axis, particle 2 is in one of these two states. Clearly, since the two possible states are different, the axis we choose to measure particle 1 along affects the properties of particle 2, contradicting our second assumption. Now we'll move on to the real experimental results. First though, note that if a particle has definite spins along each axis, then at least two of those spins must be the same. Let's look at a few examples. If a particle is up along A and down along B and C, then the pair B and C are the same. If a particle is up along A and C and down along B, then the pair A and C are the same. If a particle is down along every axis, then every pair of spins is the same. no matter what, there's always at least one pair of spins that are the same. Since there's only 3 ways to choose a pair of spins, this means that at least 1/3 of the choices are the same. Looking at the first example, the pair A and B are different, the pair B and C are the same, and the pair A and C are different. We see that 1/3 of the pairs are the same. No matter the state of the particle, at least 1/3 of the choices of pairs with spins will always be the same. In reality, there aren't particles that satisfy these facts exactly, but there are particles that have the same spin when measured along different axes 1/4 of the time. People have done many experiments on electrons and photons that satisfy these experimental facts exactly. Using our first assumption, we can drop the animation of the measuring devices and just let the squares on the left denote the spins of particle 1 and the squares on the right denote the spins of particle 2. Suppose we measure particle 1 along the a-axis. Then, by the first fact, if we measure particle 2 along the a-axis, we'll get the same result. By assumption 2, even if we measure particle 2 along the b-axis, the spin along the a-axis won't change. By our second fact, property A of particle 1 is the same as property B of particle 2 1/4 of the time. So, property A of particle 2 must be the same as property B of particle 2 1/4 of the time. Now, if we assume that the particle's spins are independent of the orientation of our measuring devices, our choice of the A and B axes is a random sample of one of the 3 pairs of axes on particle 2. With this, we can conclude directly from our previous result that properties A and B of particle 2 are the same at least 1/3 of the time. Thus, we've reached a contradiction. You may have noticed that assumption 3 encompasses assumption 2, since if all the orientations of the measurement axes are independent of all the properties of the particles, then specifically, the orientation of the first axis is independent of the properties of the second particle. However, they are useful to distinguish since breaking one or the other leads to very different types of theories. Hopefully you can see now why we started with the toy model, where there was a much more straightforward path from the assumptions to the contradiction. For the sake of completeness, I should mention that these experimental facts are slightly different from the facts used in most presentations of Bell's inequality. Usually, one uses particles prepared to be opposite, where our particles are the same, which just adds an additional negative everywhere in the argument. Above are the mathematical representations of the state, in our case and in the typical representation. Since we've reached a contradiction, one of our assumptions must be wrong. To start, let's consider what it means to deny the first assumption. First, suppose there is a theory where particles don't have properties until they interact with a macroscopic measuring device. This would break the assumption as written, since the particles wouldn't have spin independently of being measured. However, we only use this assumption to write down the results of experiments on particles. So no matter what crazy thing might be happening between the particle and measuring device, as long as it's meaningful to talk about measurements that we didn't do, assumption 1 holds. Rejecting this assumption amounts to saying that if we don't measure a property, then it doesn't exist and isn't meaningful to talk about. Not being able to talk about measurements we didn't do essentially means that we can't talk about an objective, external reality that exists independently of measurement. To see why this is such a radical stance, let's take a bird's eye view of the scientific method. Typically, science is the process of making observations, synthesizing them to make models of the world, and using those models to make new predictions, which we then test with more experiments. If the predictions are correct, that supports the model. For example, Copernicus's observations of planetary motion led him to postulate that the Sun is at the center of the solar system. This model predicts that the distance of stars will change throughout the year, which we observe. However, when we reject assumption 1, we reject the existence of an external reality, meaning that we don't believe in the Sun or the solar system or any model of the world for that matter. We simply do experiments and make predictions, without any mention of reality. This type of theory says that the only things that exist are the results of measurements. But if the measuring devices are made up of particles that don't exist, how can the measurement be real? More generally, what exactly counts as a measurement? Typically, one responds by saying that these aren't meaningful questions because they can't be tested. That naturally begs the question, why can you ask some questions but not others? One responds, of course, by saying that this also isn't a meaningful question. In sum, rejecting assumption 1 means giving up on the idea that science is a method to understand the world as it really is. Now, let's try rejecting the second assumption. Consider a theory of our toy model that has the spin of every particle pointing in one direction. When a particle goes through a measuring device, its spin and the spin of the other particle turn to point along the end the spin is closest to. For example, if we measure particle 1 along the A axis, it will go up, which will change both particle 1 and particle 2's spin. Then, when we measure particle 2 along the B axis, it will go down. It might seem like this would allow us to instantaneously communicate. Because if we decided to measure particle 1 along the B axis instead of the A axis, then particle 2 will be up along the B axis instead of down. This, however, is not possible. When particles interact with any sufficiently large object, including measuring devices, they no longer have interesting correlations with other particles. This means that we can't measure the particles before we start the experiment. If we were able to know that particle 1 was up along A and B, then we can measure it along A to make particle 2 down along B, or measure particle 1 along B to make particle 2 up along B. However, if we don't know anything about the initial state of particle 1, then measuring it won't tell us anything about the state of particle 2. It's a bit of work, but one can derive fact 3 from the rules of quantum mechanics. Essentially, all the random interactions that a particle undergoes in a measuring device change its state. This video explores that concept a little more in depth. The point is that there really are instantaneous interactions, we just can't access them. Non-local interaction might not seem that strange. After all, we send messages across the globe over the internet essentially instantaneously all the time. But that's only essentially instantaneously. The farther away an object is, the longer it takes the signal to reach it. Rejecting assumption 2 means that the signal takes no time to travel between the particles, even if they're on opposite sides of the galaxy. In fact, experiments have shown that if there are non-local interactions, they must travel faster than light. Non-locality isn't just unintuitive, it's at odds with the rest of physics, since it directly contradicts special relativity. This theory has two postulates. First, the laws of physics are the same in every inertial frame. And second, there's a maximum speed at which causal signals can travel. Recall that our second assumption says that measurements on particle 1 can have instantaneous causal influences on particle 2, which is in direct conflict with the second postulate. Relativity is one of the best tested theories in the history of science. It's the reason why gold is yellow and mercury is a liquid at room temperature. It explains how magnetic forces arise from electric ones, and it's the reason one can transfer power by moving electrons. Any theory that breaks the principles of relativity must still somehow maintain all of its predictions. To understand how we can try to match the predictions of relativity while breaking the principles, we first need to understand a little more about the theory. The heart of relativity lies in space-time diagrams, graphs with space on the x-axis and time on the y-axis. By convention, light travels at 45-degree angles, and since nothing can move faster than light, no particle's path can ever have more than a 45-degree angle. For example, this path is allowed since there's no point where the particle is moving faster than light. On the other hand, a path like this is disallowed since clearly there's a point where the particle is moving faster than light. When we start moving in everyday life, it seems like the world just shifts. On a space-time diagram, that looks like this. However, in the moving frame, one light beam looks like it's moving slower, and another looks like it's moving faster, which isn't allowed in relativity. The only type of transformation that doesn't affect the speed of light looks like this. It's not practical to give a full introduction to special relativity here, but this video series covers the basics. The relevant fact we'll use is that if two events happen at the same time in one frame, then there's a different frame where event A happens before event B, and a third frame where event B happens before event A. Now, Let's see if we can make a theory that accounts for our experiments but makes the same predictions as relativity. As a first pass, let's try rejecting just the second postulate, so particles can communicate instantaneously, but all inertial frames are still equivalent. On a space-time diagram, our experiments look like this. First, we bring the particles very far apart. Then, we measure particle 1 along the a-axis. This instantaneously changes the spin of particle 2. Finally, we measure particle 2 along the b-axis. Let's run that through one more time. In a moving frame, these same experiments look very different. In this frame, we separate the particles. Then, we measure particle 2 along the b-axis. This instantaneously changes the spin of particle 1. Finally, we measure particle 1 along the a-axis. So, in one frame, it looks like the measurement on particle 1 affects the properties of particle 2. But in a different frame, it looks like the measurement on particle 2 affects the properties of particle 1. So, which is it? Which particle affects the other? The only solution I know of is to also break the first postulate of relativity and choose a frame where the instantaneous effects occur. In this frame, everything is the same as the naive model. We separate the particles and the measurement on particle 1 affects particle 2. But, in a moving reference frame, particle 2 is affected by the measurement on particle 1 before it even occurs. This means that in some frames, effects happen before their causes. I should mention that for technical reasons, most non-local theories have particles affect each other along hyperbolas rather than straight lines. While this model technically makes the same predictions as relativity, it says that physics is not the same in all inertial frames, and that things can move faster than light. The fact that these appear to be true is nothing more than a coincidence. Going back to the example of the solar system, saying that relativity is false but just seems true is kind of analogous to saying that the Earth really is at the center of the universe, but it just looks like the planets revolve around the sun because of a mathematical coincidence. Not only that, but these theories say that we can never know exactly which frame the effects happen in, which is sort of like saying that we will never be able to have any evidence that contradicts the heliocentric model, even though it's really the Earth at the center of the universe. This is an extreme conclusion. One can view the history of science as a series of resolved coincidences. Newton explained why objects in the heavens and on Earth tend to act the same by postulating that there are universal laws of motion that every object follows. Maxwell explained why electromagnetic interactions and light travel at the same speed by guessing that light is just the propagation of electromagnetic waves. But in Maxwell's theory, the fact that the speed of light was the same for every observer was a coincidence. Einstein made this coincidence into a fact with special relativity. As a final example, Paul Dirac explained why all fundamental particles are the same with quantum field theory. But rejecting relativity means bringing in a new coincidence, a coincidence that undoes Einstein's explanation of light, Maxwell's theory of electromagnetism, and probably all of modern physics built on top of it. Now, let's consider what it means to reject our third assumption and assume that the orientations of the measurement axes are not independent of the properties of the particles. The only way I know how to reject this assumption is to say that the initial conditions at the beginning of our universe were manufactured just right so that humans would always measure these correlations between particles. We get these experimental facts not because that's the way the world really is, but because of a grand cosmic coincidence. It's like saying we have a box full of balls, and whenever we pull one out, it's red. No matter how many balls we pull out, they will always be red. But the box contains all colors of balls. The fact that we always pull a red ball out is just a coincidence. Whereas rejecting assumption 1 gave us one coincidence in the laws of physics, rejecting assumption 3 gives us thousands of fine-tuned coincidences in the initial conditions of the universe. Once again, let's take a step back and think more broadly about science. Recall that we do experiments to make models, then use those models to make predictions. When we rejected assumption 1, we said that the external world doesn't exist, so we denied making models at all. Here, there is a model, but it isn't a model of the real world, but rather some carefully constructed deception. As a result, rejecting assumption 3 means completely reimagining what it means to do science. Since we've gone over a lot, let me briefly summarize. First, we found that these experimental facts contradict these assumptions. Then, since real particles don't satisfy these facts exactly, we upgraded our facts and found that we needed slightly different assumptions to reach a contradiction. Since we're confident that the facts are correct, one of the assumptions must be wrong. Rejecting the first assumption means giving up on the idea that science makes models of reality. It's also not clear what it means for existence to depend on measurement without a clear definition of measurement. We then saw that rejecting assumption 2 means that both postulates of relativity are false, and there must be some preferred frame in which particles can communicate instantaneously. The fact that it looks like there's no preferred frame and we can't actually locate which frame it is a coincidence. Finally, rejecting assumption 3 also means giving up on the idea that science makes models of reality. So, either we reject assumption 1 or 3, which means reimagining the scientific method, or we reject assumption 2, which means that relativity is completely wrong and we need to rebuild modern physics. Neither option seems very appealing. And, either way, we need to revisit science that's been accepted for over 100 years. Unfortunately, this video doesn't end with a neat solution. On the bright side, ignorance is the engine that drives progress, and the less we understand, the more there is to discover. How bland would it be if the universe was just a simple ticking clock, and the mind of God contained no puzzles? The paradoxes of quantum mechanics aren't just mysteries, they're opportunities to learn something about the world, and perhaps ourselves.